Hello friends, I am Chandan. Today's topic is free and forced convection. This is the important topic which is asked in GATE exam. We will discuss uh, some important question which is asked in GATE exam. Okay. So question number 4. Question number 4. In this question, please read the question carefully. The properties of mercury at 300 Kelvin are density that is equal to 13529 kg per meter cube, Cp that is equal to 0.1393 kilojoule per kg Kelvin, dynamic viscosity that is equal to 0.1523 into 10 to the power minus 2 Newton second per meter square, and thermal conductivity that is equal to 8.540 watt per meter Kelvin. The Prandtl number of the mercury at 300 Kelvin is, you have to find out what is the Prandtl number. Okay, so first write down what is given in this question. Okay, what is given in this question. So in question number 4, what is given? The properties of mercury at temperature. So temperature is given T, that is equal to 300 Kelvin. Density that is equal to density rho that is equal to 13529 kg per meter cube. Cp, specific heat at constant pressure 0.1393 kilojoule per kg Kelvin Dynamic viscosity mu that is equal to 0.1523 into 10 to the power minus 2 Newton second per meter square. Thermal conductivity K that is equal to 8.540 watt per meter Kelvin. So you have to find out the Prandtl number. So how you find this Prandtl number? Okay, so the formula is, to find out this Prandtl number, the formula is Prandtl number that is equal to mu Cv by K. If you put the value, then what is the value of mu? That is 0.1523 into 10 to the power minus 2 into Cp that is 0.1393, that is equal to kilojoule, so that is 0.1393 into kilojoule, that means 1000 multiplied by 1000, okay, divided by K that is 8.540. Okay, so if you calculate this value, this value will be 0.0248. This value will be 0.0248. So this is the correct answer. So the correct answer is 0.0248, option A. Okay, now next question which is asked in GATE exam, important question, very important question. The question number 5 and 6. This is the common data type question. So read the question carefully. So here heat is being transferred by convection from water at 48 degrees Celsius to a glass plate whose surface temperature is exposed to the water is at 40 degrees Celsius. Okay, so this is the water surface and this is the glass. Okay, here the temperature is 40 degrees Celsius and in glass there is a temperature of 40 degrees Celsius. The thermal conductivity of water is 0.6 watt per meter Kelvin and the thermal conductivity of glass is 1.2 watt per meter Kelvin. The spatial gradient of temperature in the water at the water glass interface is. So here the gradient of temperature in the water at the water glass interface, that is dt by dy, that is equal to 1 into 10 to the power 4 Kelvin per meter. So what is given in this question? The value of the temperature gradient in the glass. You have to find out the temperature gradient for glass at the water glass interface in Kelvin per meter. In Kelvin per meter each. You have to find out. There is a 4 option is given. Okay. So first you have to write down what is given in this question. Okay. Now in question, there question number that is 5. What is given? There is a 2 plate. Okay. So suppose this is glass and here this is water. This is water. So here the temperature, suppose here the temperature is 48 degree Celsius and the temperature is decreasing and heat is transferred from high temperature to low temperature. Okay. Okay, here the temperature is 40 degree Celsius. Now what is given? So the thermal conductivity of water at, so thermal conductivity K of water is given. So K of water, that is equal to 0.6 watt per meter Kelvin. Thermal conductivity of glass, so K of glass, that is equal to 1.2 watt per meter Kelvin. The gradient of temperature in the water, so dt by dy, this is for water at water glass interface, that is equal to 1 into 10 to the power 4 Kelvin per meter. Okay, what is find out? So the value of the temperature gradient in the glass, so dt, you have to find out dt by dy of glass, that is equal to what? At the water glass interface. At what? Water glass interface. So so here the concept is that heat is transferred from high temperature to low temperature. Okay, in this interface there is an interface. This is the water glass interface. Okay, this is the water glass interface. In water glass interface, the heat is transferred by conduction. So heat is transferred by conduction. So heat transfer rate through water glass interface. Suppose this is Q1, heat transfer rate through water glass interface. In this side there is a Q1, in this side, and water glass interface in that side there is a heat transfer rate, that is Q dot 2. Okay, so this is the water glass interface. That's why this is the same plate. This is the water glass interface. So this water glass interface here Q1 dash, that is equal to Q2 dash, because this is the water glass interface. The heat is transferred from this side is equal to heat transfer rate to that side. Okay, so from here Q1 dot, that is equal to Q2 dot. Okay, heat transfer rate for 1, that is equal to heat transfer rate for 2. Okay, so from here this is Q1. What is Q1? That is equal to, this is the water glass interface. So this is water glass interface. So Q1, that is equal to K of water into A into dt by dy. This is the Fourier law of conduction. For Q1, that is to Kw, K of water into area into dt by dy of water, that is equal to K of glass into area into dt by dy of glass. Okay, so area and area is cancel out, and K of water, what is the value of K of water? That is 0.6. তাহলে 0.6 into dt by dy at water, that is 1 into 10 to the power 4, that is equal to K of glass, that is 1.2 into dt by dy of glass. If you calculate the value, then dt by dy of glass, that is equal to 0.5 into 10 to the power 4 Kelvin per meter. So this is the correct answer. So this is the correct answer. So here option C, that is 0.5 into 10 to the power 4 Kelvin per meter. So option C is the correct answer. Now 5 and 6 is the same question. So here the heat transfer coefficient is in watt per meter square Kelvin is. You have to find out what is the heat transfer coefficient. Okay, so heat transfer rate. So in question number 6, what is the heat transfer rate? Heat transfer rate, that is equal to heat transfer rate, that is equal to Q1 dot, that is equal to Q2. So this is same. So what is the heat transfer rate? Suppose K of G area into dt by dy G. Okay, so that is equal to K of G, that is to 1.2 into area into dt by dy of G, that is 0.5 into 10 to the power 4 10 to the power 4. Okay, this is what. Now so there is a heat transfer by convection also. So if you apply the Newton's law of cooling, then what is the Newton's law? That is Q dot, that is to H A dt, H A delta T. This is the Newton law of cooling. This is used for convection. Okay, so if you equal this Q dot and this Q dot, then H A delta T, that is equal to 1.2 into area into 0.5 into 10 to the power 4. What is the value of H? You have to find out this value of H, and A cancel out, and H, that is equal to 1.2 into 0.5 into 10 to the power 4 divided by, what is delta T? The temperature difference is 48 and 40, the difference is 8. So the temperature difference is 8. Okay, so if you calculate that value, this value will be 750 watt per meter square Kelvin. So this is the correct answer. So here answer is 750 watt per meter square Kelvin. Option D is correct. Okay, option D is correct. Okay, next question number 7. So read the question carefully. Question number 7, read the question carefully. Okay, so here in this question, for the three-dimensional object shown in the figure below. So this is a three-dimensional object. 5 faces are insulated. The 6 faces PQRS, which is not insulated. Okay, insulated means there is no heat transfer. Interacts thermally with the ambient with a convection heat transfer coefficient of 10 watt per meter square Kelvin. The ambient temperature is 30 degrees Celsius. Heat is uniformly generated inside the object at the rate of 100 watt per meter cube. Okay, assuming the phase PQRS to be at uniform temperature, its steady state temperature is. You have to find out the PQRS plate temperature, the surface temperature of PQRS. Okay. So what is given in this question? Question number 7. Question number 7. So here there is a three-dimensional object is given. Three-dimensional object is given. Okay, so this is the three-dimensional object. Okay, so this is the okay. Okay, so here this is P Q R S, this is E F G, and this is H. So the dimension is given. This is 1 meter, this is 1 meter, okay, and this is 2 meter, and this height is 2 meter. This height is 2 meter. Okay, so here what is given? So for three-dimensional object shown in the figure below, 5 faces are insulated. So there is a 6 faces is there. So this is the three-dimensional object. Here 6 face is there. Okay, and there is a 5 face which is insulated. That means PQRS that is not insulated. There is in this plate there is only heat transfer is given. Okay, there is a plate PQRS which in this plate heat is transfer from this plate to ambient, this plate to atmosphere. Okay, so the six phase PQRS which is not insulated, okay, interact thermally with the ambient with a convective heat transfer coefficient. So H is given. So what is the value of H? H that is equal to 10 watt per meter square Kelvin. The ambient temperature is 30 degrees Celsius. So the here ambient temperature that is 30 degrees Celsius. So this three-dimensional object, this is the three-dimensional object, and here this is the ambient. Okay, this side there is a ambient, this side there is a ambient. Suppose this is the three-dimensional object, this is the three-dimensional object. Okay, and this is in this plate there is a heat transfer is given, heat transfer, and other this plate, this side there is no heat transfer because this is insulated. So there the heat is transferred from this plate to surrounding. So here heat is transferred from this plate to surrounding. So there heat transfer coefficient H is given, and T infinity that is temperature of the surrounding that is 30 degrees Celsius is given. Okay, now heat is uniformly generated inside the object. So heat generation Qg that is equal to 100 watt per meter cube. Assuming the phase PQRS to be at uniform temperature, its steady state temperature, you have to find out the temperature of PQRS plate. Okay, you have to find out the temperature. Okay, how you find out this temperature? Okay, So here so there is a heat generation, that is 100 watt per meter cube. That means total heat generation, that is Q dot, that is equal to Qg, so Q dot Qg into volume, that is equal to, what is the value of Qg, that is 100 into, what is the volume, that is 1 into 2 into 2, this is the volume, length, this is the length, height, and this is the width. So 2 into 1 into 2, so there 2 into 1 into 2. So if you calculate that value, this value will be 400. This value will be 400 watt. Okay. Now heat is only transferred by convection. Heat is only transferred by convection. So Q dot, that is equal to H A delta T. Okay. So here Q dot, that is to 400, that is equal to H. What is the value of H? That is 10 into area. What is the area? So area of this plate, this is PQRS. The area is 2 into 2, 4. So 2 into 2 into delta T. Delta T means that is temperature difference. The plate temperature, this PQRS plate temperature T, and T infinite temperature, T infinite, that is 30 degrees Celsius. So T minus T infinite, that is 30 degrees Celsius. Okay, if you calculate this value from here, the T value will be 40 degrees Celsius. So here the correct answer is 40 degrees Celsius. So in this question, option D is correct, that is 40 degrees Celsius. Okay. Now next question number 8 and 9. Question number 8 and 9. Okay. Okay, read the question carefully. Read the question carefully. Read the question carefully. So here in this question, what is given? Water specific heat Cp, that is equal to 4.18 kilojoule per kg Kelvin, enters a pipe at a rate 0.01 kg per second and a temperature of 20 degrees Celsius. The pipe of diameter 50 millimeter and length, that is 3 meter, is subjected to a wall heat flux QW double dash in watt per meter square. Okay, the question is, if QW heat flux QW double dash, that is equal to 2500x, where x is in meter and in the direction of flow, x equal to 0 at the inlet, the bulk mean temperature of the water leaving the pipe in degree Celsius is. Okay, you have to find out the bulk mean temperature of water leaving the pipe in degree Celsius. Okay, so write down what is given in this question. Okay, first draw the diagram carefully. So question number 8, in this question there is a pipe is given. Okay, so there is a pipe. Okay, so this is the pipe. Okay, so this is here the pipe, this is the pipe inlet, this is the inlet, and this is the outlet, this is the outlet. Okay, so here mass flow rate. So what is given in this question? So water specific heat Cp, that is equal to 4.18 kilojoule per kg Kelvin, enters a pipe at rate, mass flow rate. What is given? Mass flow rate, m dot, that is equal to 0.01 kg per second, and a temperature of 20 degrees Celsius. The inlet temperature Ti, the inlet temperature of water Ti, that is equal to 20 degree Celsius. The pipe of diameter, what is the diameter? Diameter, that is 50 millimeter. So the diameter is here, this is the diameter, this is the diameter, that is diameter. Okay, this is the diameter, this is the 50 millimeter, this is diameter 50 millimeter, and what is given? And length, that is 3 meter. So length L, that is equal to 3 meter. So here this L, that is equal to 3 meter, is subjected to a wall heat flux QW in watt per meter square. If QW, so here QW double dash, that is to 2500 x, where x is in meter and in the direction of flow x equal to 0 at the inlet. The bulk mean temperature of the water leaving the pipe in degrees Celsius. You have to find out the outlet temperature of water. So you have to find out the outlet temperature of water. So what is given in this question? Cp, mass flow rate, and initial temperature, and inlet temperature, and diameter of pipe, and length of the pipe, and QW double dash is given. You have to find out the outlet temperature. How you find out the outlet temperature? Okay, so heat flux, that is the wall heat flux. So heat is transferred from this way. Heat is transfer periphery of this pipe. Okay, heat is transferred from this side into water through the pipe wall. Okay, so how you calculate this value? Okay, so here heat transfer, this QW double dash is given, that is equal to 2500 x. So total heat transfer Q dot, that is equal to QW double dash into area. Okay, so dq, that is equal to QW double dash into area. Suppose this is x. From this is x. Okay, in this x there is a small area, that is dx. This is dx. So this length, that is dx. Okay, so what is the area of this cross section? The pipe cross section area, that is pi d into L. So pi into d means diameter of this pipe, into L means dx. Okay, so that means dq, that is equal to 2500 x pi d into dx. So from here dq, that is equal to 2500 pi into d x dx. Okay, so the total heat, that is integration of dq, that is equal to integration of this side. Okay, so here the heat is transferred from, heat flux is this side to this side. So here L equal to 0 to L equal to 3. So L equal to L equal to 0 to L equal to 3. Okay, L equal to 0 to L equal to 3. So if you integrate this value, so q dot that equals to 2500 into pi, diameter that is 0.05 meter. So this is 0.05 into this is x square by 2, that is 0 to 3. Okay, if you calculate that value, q dot that is equal to 1766.25 watt. Okay, now heat is transfer. So there is a water is transferring through this pipe. So heat is transfer, another heat transfer rate, that is equal to m dot Cp into dt. So that is equal to q dot that equals to m. What is the value of m? 0.01 into Cp, that is 4.18 kilo. Kilo is given, that means multiply into 1000 into delta T. What is the value of delta T? That is T0 minus Ti. To minus Ti. So if you equal this heat transfer rate, that is equal to this heat transfer rate, then 0.01 into 4.18 into 1000 into T0 To minus Ti, that is 20 degrees Celsius, that is equal to 1766.25. Okay, so if you calculate that value, this value will be 76 point, so this value will be 62.25 degree Celsius. So the correct answer is 62. So here the option B is correct, 62 degree Celsius. So the correct answer is 62 degree Celsius. Now this is linked question. So question number 9. So what is given? If QW double dash that is equal to 5000, and so QW double dash that is equal to 5000 watt. 5000 watt per meter square, and the convection heat transfer coefficient at the pipe outlet, so heat transfer coefficient H, that is equal to 1000 watt per meter square Kelvin. The temperature in degree Celsius at the inner surface of the pipe at the outlet. So here you have to focus on the diagram. Okay, so this is the pipe here. This is the pipe. Okay, this is the pipe, and this is the inlet, and this is the outlet. Okay, so here the temperature Ti, and here temperature To. Okay, you have to find out this surface temperature T, this surface temperature Ts. Okay, surface temperature. So what is given? So if QW double dash that is equal to 5000, and the convective heat transfer coefficient at the pipe outlet. So this is the, so here this is the pipe outlet. The convection heat transfer coefficient at the pipe outlet, that is equal to H is given, that is to 1000 watt per meter square Kelvin. The temperature in degree Celsius at the inner surface of the pipe at the outlet. So you have to find out the temperature of the inner surface of the pipe. Okay, Ts, you have to find out this value Ts. So first you have to find out what is the total heat transfer rate, Q dot, that is equal to heat flux into area. Heat flux, that is to 5000. What is the area of heat flux? That is equal to pi into D into L. What is the value of D? That is 0.05 into L. What is the value of L? That is 3 meter. So if you calculate the value, so this is 5000 into pi into 0.5 into 3, this is what? Okay, now the heat transfer, the heat flux, heat is transfer from this heat, this is the heat flux here, so the heat transfer rate will be same as heat transfer. So heat transfer from outside to inside of this pipe is equal to heat transfer, heat gain by water. Okay, so q dot that is equal to m cp dt. Okay, so m, what is the mass flow rate, that is equal to 0.1 into cp that is 4.18 kilojoule per kg Kelvin. So 4.18 into kilojoule, that means 1000 into delta t. Delta t means T0 minus Ti. T0 minus Ti. So T0 minus Ti value, what is the value of Ti? That is 20 degrees Celsius. That is 20 degrees Celsius. Ti value, that is 20 degrees Celsius. If you calculate, so here if you equate this Q, this 2Q, then 0.01 into 4.18 into 1000 into T0 minus 20, that is equal to 5000 into pi into 0.05 into 3 into 3. So from here you get T outlet temperature of this water, that is 76.3 degree Celsius. Okay, 76.3 degree Celsius. Okay, now heat is transfer by convection. Okay, so by convection, heat is transferred by convection. So here, so from here heat is transferred by convection. So from here you can apply the equation formula, that is the heat transfer rate, that is 5. So heat transfer rate, that is equal to H A delta T. So what is the heat transfer rate? That is 5000 into pi into 0.05 into 3, that is to H. What is the value of H? What is the value of H? 1000 into area. What is the area? Area, that is pi into D into pi into D into L. Okay, তাহলে pi into D, that is 0.05 into L into delta T, that is Ts minus To. What is the value of To? That is 76.3. So if you calculate that value, then Ts value will be 81.3 degrees Celsius. So this is the correct answer. So here Ts value will be 81.3 degree Celsius. Okay, from here the correct answer is option D, 81 degree Celsius. Okay, this is the correct answer. Okay, this is the correct answer. Okay, now next question is question number 10. Question number 10. So read the question carefully. For laminar forced convection over a flat plate, if the free stream velocity increased by a factor of 2, the average heat transfer coefficient, you have to find out the average heat transfer coefficient, remains same, decreased by a factor of √2, rises by a factor of √2, rises by a factor of 4. Okay, so first of all you have to write down what is given in this question. Okay, so in this question number 10, so for laminar forced convection over flat plate, so laminar forced convection convection over flat plate. Free stream velocity. So free stream velocity, initial free stream velocity, that is v, and final free stream velocity v2. The free stream velocity increased by a factor of 2, that is 2v. Initial velocity, that is v, and final velocity v2, that is equal to 2v. The average heat transfer coefficient. Average heat transfer coefficient. Suppose initial heat transfer coefficient, that is equal to h, and final heat transfer coefficient, that is equal to the average heat transfer coefficient. So you have to find out the h2 value. H2 value. Okay. You have to find out this h2 value. Okay. So in this question there is a laminar forced convection over flat plate. Laminar forced convection means Reynolds number less than 5 into 10 to the power 5. The Reynolds number is 5 less than 5 into 10 to the power 5. Okay. The formula, that is if Reynolds number less than 5 into 10 to the power 5, then there is a formula. You have to remember this formula, that is Nusselt number, that is equal to 0.664 into Reynolds number to the power 1 by 2 and Prandtl number to the power 1 by 3. Very, very important formula. This is very, very important formula. The Nusselt number, that is equal to 0.664 Reynolds number to the power 1 by 2 and Prandtl number to the power 1 by 3. And you know that Nusselt number, that is equal to HL by K. You know that Nusselt number, that is equal to HL by K, and Reynolds number, that is equal to rho VL upon mu. Rho VL upon mu. So from here, Reynolds number, that is equal to mu by rho, that is equal to nu. So VL by nu. VL by nu. Okay. So from here you can write that Nusselt number, that is HL by K. HL by K, that is equal to 0.664 Reynolds number, that is VL by nu. VL by nu to the power 1 by 2 and Prandtl number, that is equal to mu Cp by K, that is Prandtl number to the power 1 by 3. Okay. Okay. From here H proportional to v to the power 1 by 2. So H proportional to, you have to find out the relation H proportional to v to the power 1 by 2. H proportional to v to the power 1 by 2. So from here you can write that is H2 by H1, that is equal to V2 by V1 to the power 1 by 2. That is equal to H2. What is the value of H1? That is H that is equal to V2, that is 2V to the by V1, that is V to the power 1 by 2. From here H2, that is equal to root 2 into H. So this is the relation. Okay. So what is given? The average heat transfer coefficient. The average heat transfer coefficient rises, option C, rises by factor of root 2. That is H2, that is equal to under root 2 into H1, initial heat transfer coefficient. H1, that H means H1. So this is the initial heat transfer coefficient. So root 2 times. The root 2 rises by a factor of root 2. So option C is correct. Okay. Now question number 11. This is very, very easy question. Just read the question carefully. Okay. So in this question what is given? In the laminar flow of air, Prandtl number that is equal to 0.7 over a heated plate. If delta and delta T denotes respectively the hydrodynamic and thermal boundary layer thickness, then what is the relation between delta and delta T? Delta is hydraulic boundary layer thickness. So delta is hydraulic boundary layer thickness and delta T is thermal boundary layer thickness. Delta T is thermal boundary layer thickness. You have to find out what is the relation between hydraulic boundary layer thickness delta and thermal boundary layer thickness delta T. Okay, so first write down what is given in this question. So question number 11. So in the laminar flow over air, so in the laminar flow of air, Prandtl number that is equal to 0.7 over a heated, if delta and delta T, delta is given and delta T is given. Delta is hydraulic boundary layer thickness, hydrodynamic boundary layer thickness, and delta T that is thermal boundary layer thickness. Okay, you have to find out the relation between hydrodynamic boundary layer thickness and thermal boundary layer thickness. Okay, so the relation is Prandtl number that is equal to hydraulic boundary layer thickness and thermal boundary layer thickness to the power cube. Okay, so from here, that is Prandtl number, from here, so Prandtl number to the power 1 by 3, that is delta upon delta T. Okay, from here Prandtl number that is 0.7 to the power 1 by 3, that is equal to delta by delta T. From here delta that is equal to 0.88. If you calculate that value 0.7 to the power 1 by 3, that is 0.88 delta T. That means delta less than delta T. Delta less than delta T. That means delta T is big as compared to delta. So thermal boundary layer thickness is greater than hydraulic boundary layer thickness. So from here you can conclude that the option C, delta less than delta T, thermal boundary layer thickness is greater than hydraulic boundary layer thickness. That means hydrodynamic boundary layer thickness, that is thermal boundary layer thickness is greater than hydrodynamic boundary layer thickness. So option C is correct. Okay, now next question is question number 13. Question number 13, very very important question. Just read the question carefully. Question number 13. Read the question carefully. Just read the question carefully. Okay. So what is given in this question? So here, what is given in this question? From here, a fluid Prandtl number that is equal to 1 at 500 Kelvin flows over a flat plate of 1.5 meter length, maintained at 300 Kelvin. The velocity of the fluid is 10 meter per second. Assuming kinematic viscosity nu that is equal to 30 into 10 to the power minus 6 meter square per second. The thermal boundary layer thickness in millimeter at 0.5 meter from the leading edge is. You have to find out the thermal boundary layer thickness in millimeter. in millimeter at 0.5 meter from the leading edge. Okay, how you calculate the thermal boundary layer thickness? Okay, first of all we have to write down what is given in this question. Okay, you have to write down what is given in this question. So here this is question number 13. This is question number 13. In question number 13, what is given? A fluid Prandtl number, that is Prandtl number is given, that is equal to 1 at 500 Kelvin flows. So T infinity temperature, that is 500 Kelvin over a flat plate of 1.5 meter length. So length of this flat plate, that is 1.5 meter. Maintain at temperature Ts, that is 300 Kelvin. Surface temperature, flat plate temperature, that is 300 Kelvin. The velocity of the fluid, that is 10 meter per second. As assuming kinematic viscosity nu, that is 30 into 10 to the power minus 6 meter square per second. The thermal boundary layer thickness, you have to find out the thermal boundary layer thickness, that is equal to what? At 0.5 meter from the leading edge. At 0.5 meter from leading edge. Okay. So first of all, suppose this is a plate. The surface temperature of this plate, that is Ts. Surface temperature, that is Ts. And there is a fluid temperature, that is 500. So T infinity, that is 500 Kelvin. The fluid is flowing over the flat plate. Okay, the fluid is flowing over the flat plate. Okay, so from here what is given? So first of all you have to find out delta T, thermal boundary layer thickness. Thermal boundary layer thickness at 0.5. So this is the plate. Here this is the leading edge and this is the trailing edge. Okay, so what is the leading edge? This is the leading edge. You have to calculate what is the thermal boundary layer thickness at 0.5. So suppose this is 0.5. This is 0.5 meter. So you have to find out thermal boundary layer thickness at 0.5 meter from leading edge. This is the leading edge. From in this location you have to find out the thermal boundary layer thickness. Okay, so if you calculate thermal boundary layer thickness, you have to determine this flow is laminar flow or turbulent flow. If you check this flow is laminar flow and turbulent flow, you must remember the Reynolds number formula, that is rho VL upon mu, that is equal to VL upon nu. Mu by rho, that is nu, that is kinematic viscosity. Okay, if you calculate that value, V means 10 into length, that is length. Just you have to calculate in this location a Reynolds number in that location, that is 0.5 meter from leading edge. So length, that is equal to 0.5 by nu, that is 30 into 10 to the power minus 6. 30 into 10 to the power minus 6. So 30 into 10 to the power minus 6. If you calculate that value, this value will be 1.66 into 10 to the power 5. This value will be 1.66 into 10 to the power 5. But if this value is less than 5 into 10 to the power 5, this is the critical critical Reynolds number. This is the critical Reynolds number. This is less than 5 into 10 to the power 5. So that means from here you can say that the flow is laminar flow. You can say that flow is laminar flow. Flow is laminar flow. If this is laminar flow, then hydraulic boundary layer thickness, hydrodynamic boundary layer thickness, that is equal to, the formula is 5x by under root Rex. Okay, so 5x, 5 into x value, what is the value of x? That is 0.5. What is the value of x? That is 0.5. 0.5 by under root Rex. What is the value of Reynolds number at location x? At location x, the Reynolds number, that is equal to under root Rex, that is 1.66 into 10 to the power 5. Okay, if you calculate that value, this value will be, hydraulic boundary layer thickness will be 0.00612 meter. Okay, if you calculate the value, this value will be 0.00612 meter. Okay, now one relation is there, thermal boundary layer thickness and hydraulic boundary layer thickness and Prandtl number. There is a relation delta T, thermal boundary layer thickness delta T by hydraulic boundary layer thickness, that is equal to 1 by 1.026 Prandtl number to the power minus 1 by 3. From here you have to find out the thermal boundary layer thickness. Thermal boundary layer thickness, that is hydraulic boundary layer thickness. What is hydraulic boundary layer thickness? 0.00612 by 1.026 Prandtl number. What is given the Prandtl number? That is equal to 1. That is equal to 1. So here Prandtl number 1 to the power minus 1 by 3. So if you calculate, this is 1 to the power minus 1 by 3, that means 1. So if you calculate that value, 0.00612 divided by 1.026, then this value will be 5.97 millimeter. If you multiply this, the answer will be 5.97 millimeter. Actually this answer will be 0.00597 meter. You get this value 0.00597 meter. From here, if you multiply this 1000, multiply to this 1000, then 5 into 97, 5.97 millimeter. So here the correct answer is 5.97 millimeter. Okay, so here in this question there is a thermal boundary layer thickness in millimeter at 0.5 from the leading edge, that is 5.97. Okay, so this is the correct answer, 5.97. Okay, now there is a last question, question number 17. Question number 17. Okay, read the question carefully. Question number 17. Read the question carefully. So here in this question, just read the question carefully. Question number 17. A thin vertical flat plate of height L. This is the flat plate. The height of this plate, that is L, and infinite width perpendicular, infinite width of this plate, that is infinite, to the plate of the figure is losing heat to the surrounding by natural convection. The temperatures of the plate and the surrounding are the properties of the surrounding fluid are constant. The relationship between the average Nusselt and Rayleigh number is given as Nusselt number, that is equal to K into Rayleigh number to the power 1 by 4. where K is a constant. The length scale for Nusselt and Rayleigh number are the height of the plate. The length scale for Nusselt and Rayleigh number are the height of the plate. The height of the plate is increased to 16 L. The initial height that is equal to L and the final height that is increased 16 L, keeping all other factor constant. Okay, so this is L and this is the vertical plate. So the question is that if the average heat transfer coefficient for the first plate, that is H1, and that of the second plate, that is H2, the value of the ratio H1 by H2. You have to find out the value of this ratio, that is H1 by H2. So how you calculate this value? How you calculate this value? So if you see the question carefully, then there is a relation is given, that is Nusselt number that is equal to K into Rayleigh number to the power 1 by 4. K into Rayleigh number to the power 1 by 4. So what is given in this question? Question number 17. Question number 17. Question number 17. What is given? That is Nusselt number that is equal to K, that is constant, and Rayleigh number to the power 1 by 4. Okay. And what is given in this question? The initial length, the length scale for the Nusselt number are, so initial length L1 that is equal to L and L2 that is 16L. Okay, you have to find out what is the value of H1 by H2, that is equal to what? Okay, so Nusselt number that is equal to K into Rayleigh number to the power 1 by 4, and we know that Nusselt number that is equal to HL by K, and Rayleigh number that is equal to Grashof number into Prandtl number. Rayleigh number that is to Grashof number into Prandtl number, and we know from Grashof number that is equal to G beta L cube delta T by nu square. You have to remember this formula, Grashof number that is equal to G beta L cube delta T by nu square. G beta L cube delta T by nu square. If you put this formula, that is Nusselt number HL by K, HL by K, that is K is constant into this K is constant, Rayleigh number that is equal to Grashof number into Prandtl number, that means Grashof number into Prandtl number to the power 1 by 4. From here, that is HL by K, that is equal to K, this is the constant value, and this is the conductivity, thermal conductivity. Okay, conduction heat transfer coefficient. Okay, this K is conduction heat transfer coefficient, and Grashof number, what is the formula of Grashof number? G beta L cube delta T, G beta L cube delta T upon nu square into Prandtl number, mu should be by rho, but this is only Prandtl number. Okay, that is 1 by 4. You have to find out the relation between H and L. You have to find out this relation between H, this H and L. Okay, so from here you can see that H and L that is proportional to L cube whole to the power 1 by 4. Then L to the power 3 by 4. L to the power 3 by 4. From here L to the power 3 by 4. Okay, so from here H proportional to L to the power 3 by 4 minus 1. From here H proportional to L to the power minus 1 by 4. From here H proportional to 1 by L to the power 1 by 4. 1 by L to the power 1 by 4. So this is the relation between H and L. This is the relation between H and L. From here you can write the formula, that is from here you can write H1 by H2, that is to L2 by L1 to the power 1 by 4. So from here L2, what is the value of L2? That is 16L. 16L by L to the power 1 by 4. 16L, that is 16 to the power, L cancel out, this L cancel out. Okay, 16 to the power 1 by 4. 16 means 2 to the power 4 into 1 by 4. 4 cancel out, that is equal to 2. So here this H1 by H2 is equal to H1 by H2, that is equal to 2. So the correct answer is 2. So here the value of the ratio H1 by H2, that is equal to 2. Okay, so this is all important question of free and forced convection. So thank you friends, thank you everyone, bye bye.